Okay, so we are starting the second half of this section, this chapter. So it is a totally different topic. So let's think about Starbucks coffee. So grande iced coffee is supposed to be 16 ounces. Maybe I used this similar example in an earlier chapter, and I was inspired by a news about lawsuit someone filed against Starbucks because there are too much ice but little coffee, less coffee than 16 ounce. But I remember Starbucks won the lawsuit. It's not weird. The kind of natural decision. Anyhow, so it doesn't need to be Starbucks. So I am testing. I am FTC agent, and I want to test if the product is correctly labeled, like it's following the rule, like advertised, selling the product that is as advertised. Okay. Now, let's apply the hypothesis testing rule here. I believe that Starbucks coffee is correctly 16 ounces. That is the coffee is supposed to be 16 ounces. But actually, then that means I'm going to reject the null hypothesis if the sample average is different from 16. So then I'm going to reject the null hypothesis and I will punish the coffee shop. Does it make sense? Actually, no. Because I don't need to punish the coffee shop if the amount is more than 16 ounces. Selling more than 16 ounces, so advertise as 16 ounces, but actually it contains more than 16 ounces, it's not a problem. So then our framework is limited. Does not work in this case. What we want here is we want to reject only when the actual amount is lower than advertised, right? So we are going to change our notation like this. Either way, the different textbooks use different notation. So you may think it like this. So you believe that the amount is exactly 16 ounces, but you are going to reject that if the actual amount is less than 16 ounces. More than 16 ounces is not a problem or will not happen. You don't believe it would happen. Oh, anyhow, I don't care. Greater than 16 is none of my business, right? So I will only compare whether it is exactly 16 or less. Or you may think it this way. I believe the amount is at least 16 ounces. Of course, there is no reason to give more than 16 ounces, but anyhow, this is my belief. But I'm going to reject my belief if it is strictly smaller than 16 ounces. In any case, in both cases, in both notation, basically what I'm saying here is the key idea is I'm going to punish the coffee shop if the amount is less than advertised, right? But more than advertised is not a problem. That is not the problem at all. So I will reject only on the lower side. That is the main idea. And this is actually more common example. If you look up, I look at a lot of textbooks to make up quiz questions, but it is more difficult to find examples with equality. Inequality is easy to find. Okay, anyhow, let's. So we call this one-tail test because we are rejecting only on one tail. We are interested in rejecting only on one tail. So you may think about upper tail test or lower tail test. What we just saw was lower tail test because we are going to reject only on the lower tail. Upper tail is not my business. I don't care, right? So, but in other cases, you may need to reject if the sample is too large. If the sample average is too large, you may want to reject. Then it is upper tail test, but it is exactly symmetric. So identical with different direction of inequalities. So it shouldn't be that much different. Basically, they are the same thing. So here in this example, I'm going to consider this case, right? So we will reject if x bar sample average is too small. Okay, that is natural in our context. So then let me explain the idea with graph. So we believe the truth is 16 here, right? So assume that my belief is correct. So the sample average is generated based on the distribution around 16. But if the sample average is too small, smaller than 16, you need to suspect if the coffee shop is selling lower than expected. So more suspicious only on this direction. That is the key point. You are making it more suspicious only on this direction. So this direction has no problem. There is no suspicion at all here, right? Only one directional arrow. So we are going to calculate p-value this way. So when you observe x bar here, in the previous chapter, we calculated p-value using probability on both sides, right? Do you remember that? So p-value is not only here but also there because both sides are equally suspicious. That was our key idea. But in this example, I don't care this side. There is no suspicion in this side. So you are calculating p-value only on this way, this tail. So that is p-value. That means now one-tail test p-value is only half of the two-tail test, right? So because the other side probability is not included in the p-value, right? That is truth. And critical value happens only on one side. There is only lower critical value. Critical value only on the lower side. So rejection region forms only on the lower tail. There is no rejection region on the other side. As I keep saying, I don't care this side. So critical value is only on here. So then let me summarize. First, t statistic has no direction. There is no directional implication here, so there is no difference. T statistic is calculated in the same way. It is the difference, standardized difference between the belief and the data. That is interpretation of the t statistic. And then based on the t statistic, we calculate the p-value, probability of more suspicious outcomes. But two-tailed test has both sides, lower than or greater than, lower than minus t-stat, and greater than plus t-stat. But now, upper tail test only includes upper tail probability. Lower tail test includes only lower tail probability. Okay? So, it is much easier. And exactly half of the two-tail test p-value. But the decision rule is the same. P-value, the null hypothesis is rejected if the p-value is smaller than alpha. So that means, even in the same data, the decision, rejection could be different. One may be rejected or not, depending on whether your test is one-tailed or two-tailed. Right? Because p-value is different. That is possible. Maybe we are going to see examples later. Okay? And t-statistic approach. As I said, t-statistic itself has no direction, so it is the same. But what changes is the decision rule. Now, in the two-tailed test in the previous chapter, t-statistic, the null hypothesis is rejected if the t-statistic is too small or too large, right? But now in one tail, it happens only on one direction. However, the cutoff, the threshold should change because, so earlier, significance level alpha is a probability, so a type 1 error probability that is split on both tails. But now they don't split on both tails, but they are accumulated on one tail. So like earlier, we had z alpha over 2 plus side, minus side, because each tail probability is alpha over 2. But now, alpha is, all the probability alpha is put only on one side. So, instead of alpha over 2, we are using Z alpha. Subscript alpha is the new threshold. So this is the difference. By the way, of course, the direction of the inequality and the sign, whether it is plus or minus, follows from the direction of your test. So that is more natural, trivial if you understand what you are doing. So I'm not going to care much about that, but what is more important difference is alpha here, probability. Finally, critical value approach. Critical value approach was given like, critical values are given like this. So your belief plus minus something multiplied by standard error. First, difference is the direction. You have to determine the sign. And also alpha over 2 is replaced by alpha. Everything else is the same. So when you have upper tail test, you have to set critical value greater than your belief. So belief plus something. And lower tail test has belief minus something. But that value is, but Z alpha is used instead of Z alpha over 2. And of course, the inequality rejection region is determined based on the direction of your test. This is also intuitive. Okay, so you may think it's a minor change, but also it is confusing change. Let me compare, especially this part is the most confusing ones. Z alpha over 2 was the common numbers we have used earlier. Like we use them for confidence intervals and two-tail tests. However, Z alpha is for one-tail test, which is different from the earlier numbers. So this is the comparison. So when you use 10% probability, significance level, that means each tail has 5%. So in two-tail test or confidence interval, you had 1.64. So top 5% value is 1.64, bottom 5% is minus 1.64. However, now that number is used for 5% because all the 5% is put on one side. So your number should be 1.64. So the number is now decreased. Given the same significance level, you are decreasing the numbers. Or that means you are more likely to reject, right? Which is clear because p-value is halved. That means you are more likely to be rejected, right? Your belief is more likely to be rejected because the p-value should be greater than alpha for the belief to be accepted. But p-value is now smaller, so more rejected, which happens also here. This number is smaller, so the difference must be smaller, or the sample average must be closer to your belief. So everything is more strict because we are considering only on one side, right? Considering one side gives you some advantage. Okay, so now we suppose some numbers like these. So we observe 100 observations and sample average and standard deviation. Now let's calculate t-stat, p-value, and critical value in this lower tail test, right? Starbucks example, grande coffee example. First, t-statistic has no difference. Your data sample average is 15.6. Subtract your belief, and the difference is standardized by standard error, standard deviation, sample size. So you get minus 1.33. So the observation is minus 1.33 lower than your belief in terms of standard normal scale. And p-value. P-value is now different. P-value is only on one side, smaller than 1.33, which if you calculate from Excel, you will get about 9%. Okay? So that means 9% will be rejected if your significance level was 10%. But it will be, the null hypothesis will not be rejected if the significance was 1 or 5%, lower than 9%. Okay? So decision making is the same, but this calculating the p-value is different. Only among these steps, 3 steps, only this line is the difference. Okay? And now if you look at the t-statistic is now minus 1.33. Now let's compare the thresholds change. If you use 10%, the threshold is 1.28. Here, look at these numbers. So 1.28, 1.64, 2.33. So take them. By the way, of course, you have to take minus sign in front of them. So minus 1.33 is lower than this threshold. I mean, too low. But in 5% or 1%, the threshold is further away from the zero more than your t-statistic. So t-statistic is close enough to 0, so you don't reject the null hypothesis. So the decisions are consistent with p-value approach. Now, critical value approach. Critical value forms only on the lower side. So belief minus something, but in something, you are using the same number, z alpha again. So this z alpha are these numbers. So use these numbers again. Then you get these critical values. Okay? So your sample average is 15.6, which is lower than your critical value at 10%. Right? However, this sample average is greater than, it's okay when you compare to these critical values. Right? Your standard is much more generous at 5% or 1%. Okay? So as you see, the 3 approaches are basically, ideas are the same, but you need to check the signs, the direction of the inequality, and alpha. These 3 main changes are confusing, minor changes, but pretty confusing. So make sure you are doing it correctly. Okay, now some exercises. So now I will change the story a little bit. So iced coffees must be served at a temperature 40 degrees or lower. I think, yeah. And so that means lower, like if it's too cold, that is not a problem. It is iced coffee. But the problem is, if it's not cold enough, then it is a problem, right? So we observe 100 sample, and sample average is 40.7 degrees, and standard deviation is 4 degrees. What is the p-value? Calculate here. And also, by the way, note that the direction of inequality is now greater. So it's upper tail test. Keep that in mind when you calculate the p-value. Okay, let me show you the answer. You do the algebra. First, you need to calculate the t-statistic, which is 1.75, right? Sample average minus your belief standardized by standard error, 1.74. And now you calculate the p-value only on the upper tail. So only calculate probability greater than 1.75. That is 4%. So p-value is 4%. Then now I will let you calculate the critical values. Again, it's upper tail test. All the numbers are the same. Use 5% significance level to calculate the critical value. Okay, so let me show you the answer. First of all, we are doing upper tail test. So your critical value must be greater than 40. So these two answers are automatically wrong. They may be used for lower tail test, but not here. Okay, we are worried about if the temperature is too high, so these two are not a problem. Okay, critical values go like this. Your belief And because it is an upper tail test, you have to add something. And this number is 1.64 because we are using 5% significance level and standard error, kind of standard. So if the sample average is higher than 40.656 degrees, then you need to worry about the temperature. It's too high. Okay. So in any case, in both cases, we are going to reject the null hypothesis. So here critical value is 40.6565, but your observation is 40.7, which is higher than the critical value, so you reject the null hypothesis. It is too high. Also here, p-value is 4%, which is lower than 5% significance level, so you reject the null hypothesis. So if either you use p-value or critical value, the null hypothesis will be rejected at 5% level. Okay, the next step is to calculate error probabilities, but the video becomes too long, so I'm going to stop here, and maybe in the next video we will do these error probabilities and another example. Okay, see you there.